is one of the few people who's spent his whole career at one institution. He did his BS degree at the Indian Institute of Technology, graduating with honors, and then he came to the U.S. and did a master's degree in mechanics, and ended up at Northwestern, where he did his PhD under Lynn Johnson. And Lynn has a University of Utah connection. He was a PhD student under my father, so it's kind of fun that Lynn mentored Professor Virkar, and then Professor Virkar has mentored me. He came to Utah 5 decades ago, and at the time he came, the University of Utah was just starting work on a sodium-sulfur battery needing a beta double prime aluminum electrolyte manufacturing facility. And Ron Gordon, who started this with Al Sosin, didn't have any background in beta alumina. They just jumped right in. The work had been done by Neil Weber and Joe Kummer at Ford, and so they learned how to do it. And Anil was instrumental in them being successful, and he ended up helping to co-found a company called Ceramatech that lasted for a few decades. Coors Tech took it over, and he and Dinesh Shetty, who's also here, they founded a company called MSRI that did work on fuel cells, and Anil worked with another company on fuel cells that has been successful, and he's also founded a company on nano-oxides. He is a brilliant scientist, but he's an excellent teacher, and he's an inventor. And he's got a whole list of honors. I'm not going to talk about all of those, but he has got the Outstanding Research Award from the University of Utah in 1994. He's a fellow of the American Ceramic Society. He's a fellow of the ASM, of Electrochemical Society. He's a National Academy of Science. He's an Inventors Award. He won the Ross Coffin Award from American Ceramic Society. We are so fortunate to have him as a faculty member, and he's finally decided he's going to retire. And we are so thankful to have him come today, and we'll turn the time over to Professor Anil Virkar, distinguished professor.
Let's see, what would I do here?
Quick, right up there by you.
Close by. Okay. And this goes, this
You can just advance
with this, right? Okay, perfect. Thanks very much for coming. And I just want to tell you that Professor Kettler and myself, we have worked for many, many years, published a number of papers. Professor Shetty and myself, I also worked on many, many papers. Okay. My collaborator on the technical part here is Professor Xiaodong Zhao. He is of the University at Connecticut, and he was at University of Louisiana. That's why Professor Shetty asked me that question. So the title is Thermodynamic and kinetic considerations concerning stability and activity of core shell and alloy catalysts for proton exchange on your shell side. And it's a long title. Now let's see. Okay. My first 2 slides are the most important of this stuff. Okay? Rest doesn't matter. All right? Okay. I list my mentors. One of the greatest things I found in my career is having good mentors is what makes you successful. So I just want to tell you, my father received PhD in organic chemistry in 1942. That was 2 years before I was born. My uncle was Surgeon General. I mean, let's say, my grandfather from my mother's side received a bachelor's degree in mathematics, I think about 1910. And then he was the mayor of a town. Professor Morifine, even though he was not my advisor, he was the, I would say, not just my greatest guide, this thing, and he is the founder of the first material science department in the world. He is the one who coined the term. So this kind of, Professor Ron Gordon hired me here at the University of Utah as a postdoctoral fellow in '73, and he and his wife guided myself and my wife throughout the career, and in various aspects, jobs, workplace, social, friendship. Professor Anil Virkar, Professor Cutler's father, and we worked together quite a bit. He also guided me a lot, and we published a number of papers together, a number of patents together. And I think one of the things that I want to say is that having great mentors is critical to your success. So it doesn't have to be science or engineering, it could be anything, social, personal. So mentoring is important, and as the end of my career, I can really tell you that how important that is. Okay. And here I just want to show a photo. It's going to tell you my photo with Professor Morifine at Northwestern on April 12, 2013, on his 95th birthday. So tomorrow, if he had been alive, he would have been 104 years old. Okay, he died at the age of 97. Those were the days where you retired at the age of 65. You had no choice. So after the age of 65, he was Professor Emeritus for 32 years. And he used to go 3 to 4 times a week to school. And when I asked him, how do he go? He says, sometimes I hitch a ride. At his birthday party, said. And then one week, he didn't show up. And then 3 days went by, and then somebody from the department went. And they went to his house, and he had died during his sleep. But I mean, he could live alone up to the age of 97, because his wife had passed on earlier. So what I think is, I'll talk about technical part, the rest of it, but I really believe these personal relationships are so critical to your own success. Okay. I'm showing you a schematic of a PEM fuel cell. PEM starts from proton exchange membrane. It contains a polymeric membrane called Nephron. It conducts protons. So on one side, you put fuel in, which is hydrogen. Other side, you put air in, which is the oxygen. This is the cathode, this is the anode. I think one question I have. Have you ever taken thermodynamics? Okay. And kinetics? Yeah, good. And so basically what you're generating is your protons transfer from hydrogen decompose into protons and electrons, protons transfer through the membrane, electrons go here into the external circuit, come back here, oxygen comes in, react with oxygen to form water vapor. So basically what you're doing is oxidation, the net reaction is hydrogen plus half oxygen giving you H2O. And as you know, maximum work is the decrease in the free energy maximum. So of course, so this is the guiding principle. So basically you are reacting hydrogen and oxygen, but you're doing it electrochemically, so you are generating electrical current. I'm going to show you here a photograph of Toyota Mirai. I lived there more than 50 years, almost more than 51 years. And I loved living in Utah, so you can tell that I'm in here. But if I were living in California, I would buy this. And I'm going to tell you that depending on where you live, another 15 years, you will have hydrogen car. Japan is putting enormous amount of resources for hydrogen car. Right now, hydrogen car is by far the most ideal car. Problem is we don't have hydrogen infrastructure. That's where the issue is much of the time. Okay. Now this is the outline of my talk. I'm going to talk about. By the way, when the time is close to, just tell me and I'll switch to the last slide. Okay. Okay. Let me go back to this. How do I go back? Oh yeah. Okay. I just forgot to mention one thing. In this one, both sides, the catalyst is platinum. Okay? The platinum dispersed on carbon is the catalyst for both the cathode and the anode. Okay. So I'm going to talk about mechanisms of catalyst degradation, role of thermodynamics in durability of catalysts, how the thermodynamics play a role, alloy and core shell catalyst, role of catalyst size distribution, role of support. I mean, the particles have to sit on carbon, so that's the support. And I'm going to talk about how we can achieve increased stability and increase activity. Okay. I'm showing you here a schematic to describe the mechanism of catalyst degradation. This is how a schematic of a catalyst looks like. This is a carbon support, and these black dots are platinum particles. A number of things can happen. One thing that can happen is these particles simply detach from carbon. And if they detach, they are not electrically active anymore. Other thing that can happen is they can agglomerate. If they're too close, they'll sinter together to agglomerate. And even if they are far apart, they can do what's called Ostwald ripening or coarsening that can occur. So there are various mechanisms by which this occurs. In addition to that, platinum can ionize and can actually precipitate, go inside the membrane from cathode, and they can precipitate in it. What that does is you're losing catalyst. These are various mechanisms of degradation. Okay. Since you have taken thermodynamics, you know what chemical potential is. Now, of course, we typically talk about chemical potential of bulk materials. But here, talk about nano-sized particles. So you have to take into account the fact that it's a small particle with surface energy in it. So the chemical potential of a particle of radius r is given chemical potential of bulk platinum, what you say large nanomolar basis, plus 2 times the surface energy that the molar volume of platinum and the radius of particle. So you can see if the particle is very, very small, its chemical potential is high. This free energy is high. And if we know, all things want to go to low free energy, basically. So we need to have the catalyst small enough so that it is active, but we have to prevent it from making bigger, so it's no longer active. And it wants to go bigger because of lowering the free energy. Okay. There are many equations here. As I said, anybody can look them up. I'll just kind of go through, and I don't want to go dwell too much on the equations per se, but something I do need to. So just want to tell you, at room about 80, these are about 80 degrees, bulk platinum, 300 degrees, bulk platinum, the Gibbs free chemical potential is minus 147.75 kilojoules per mole. Okay. If you take a nano-sized particle of 1 nanometer radius, then you have to take into account this part plus this term, which takes the surface energy and the radius of the particle into account. Assuming some numbers, the calculated chemical potential of a nano-sized particle, 1 nanometer, is minus 120 kilojoules per mole. Remember, minus 120 is larger than minus 147. Okay, number wise, magnitude wise. If you are a scale, minus 147 is low. Minus 120 is high. Right? So that's the reason these particles want to coarsen and do that to get to the bulk value. So higher the chemical potential, the lower the stability. And as I said, the smaller the particle, the higher the chemical potential. Okay. So let me tell you how, as I mentioned, for a catalyst to work, it sits on a carbon support, and these are particles. Now this membrane is called an ionomer, which only contains, by and large, only contains hydrogen ions. Or any ions, basically, to some extent. Now, to coarsening, you have to take platinum from here to here. But to do that, electrons can't flow through that much at all. So how does it happen? Platinum here, smaller particle, dissociates with platinum 2 plus 2 electrons. Platinum 2 plus goes through across here. Electrons go through here, and they meet again. And the reverse reaction occurs where platinum 2 plus 2 electron become platinum. So then that reaction is transferring platinum from a smaller particle to a larger particle. That's how the coarsening occurs. And if it is in direct contact, just platinum goes to again the ionomer, electrons just directly go through it. This is an interesting. Support must be electrically conducting for growth to occur. As well show you, there is no growth in alumina if it's alumina. But support must be electrically conducting to function in the electrodes. So you have catch-22. I don't know, do you know the term catch-22? Sorry, it's a really old term. Where you're stuck, basically. You're sure. So if the particles isolated, however, they're different. Okay? No, there's no support. Initially what happens is platinum ions go from smaller particle to larger particle, but there is no transfer of electrons. So the larger particle becomes positively charged, this becomes negatively charged, and then basically what's called electrochemical potential, when they become equal, there is no further growth. So isolated particles don't grow. But isolated particles don't work as an electrode either. So you have a... Correct. So here I'm showing some transmission electron micrographs of commercially received platinum by a company called ETAC, supported on carbon. This is a TM micrograph. This is the carbon, and these are black dots, the platinum. I'm just showing the same one here with a larger image. Again, this is the platinum, and this is carbon sitting on it. If you put it 1 week in nitric acid, there's slight growth because there's not much dissolution of platinum in nitric acid. You might make the particle. But if you take and put 1 week in platinum tetrachloride solution, enormous growth occurs. You can see from here to here, substantial. The reason I'm choosing giving the reaction as PT2 plus, because that's the main reaction that occurs. But if you hate PTCl4, there's always a small amount of PTCl2 in it. The solution that you're going to use is PTCl4. But the one that's active is PT2 plus, not PT4 plus. Okay. Now we actually did this work by using platinum and on aluminum oxide as a catalyst. This catalyst is used for chemical reactions, not for electrochemistry. There are many chemical reactions that use platinum and aluminum oxide. But so the same thing, 1 week in platinum chloride solution, there is no growth. Because you cannot transfer electrons. There's no way to transport electrons. The aluminum oxide is perfect insulator. In fact, what happens is not only that growth doesn't occur, somehow the platinum dissolves into the platinum chloride solution by this reaction, PTCl4 plus PT to form PTCl2. So actually, even I don't know if you can tell with naked eye, actually there is more platinum here than here. Because it just dissolves, slightly. Okay. So I'm going to talk about role of thermodynamics in degradation and durability. Dissolution and reprecipitation of platinum. Platinum 2 plus concentration dictates the kinetics of transport and therefore the kinetics of degradation. Chemical potential of platinum in the catalyst determines PT2 plus concentration in the ionomer liquid. The higher the chemical potential, the faster they go. So smaller particles want to become bigger. Oxidizing atmosphere, you have higher PT2 plus concentration. Reducing atmosphere, very low because basically platinum. So that's, as a result, cathode, it degrades, but anode doesn't degrade. The anode is hydrogen. There's no enough oxygen to form that. By the way, you can stop me anywhere and ask questions. You just kind of casual thing. Okay. Now, platinum is expensive. So one of the ways people try to do is to reduce its cost is to alloy the platinum with something else. So that way can reduce it. And so We're going to talk about role of alloying elements, chemical potential of platinum, role of alloying elements in the degradation involving dissolution depletion. And there's an enormous amount of work done. Much of this work that I'm talking about was done about before 2014. But I had a couple of students after that. They had done an enormous amount of work that I'm not talking about. Alex Zendi was the last student who had worked on platinum catalyst with me. He works for Micron. And Li Xiang was one of the students who did palladium catalyst as well. Never got around to publishing it. Okay. So alloy catalyst. As I said, the reason we want to use alloy catalyst is because platinum is so very, very expensive. So I'm showing you here small particle, large particle of alloy catalyst. So what happens in smaller particles in the solution or liquid, leaching occurs of both platinum or alloying element. It's kind of dissolved into it. Then what happens, and here initially that happens here as well. But after a while, what this platinum does is deposits on this larger particle. And I'm not showing you carbon here, but there's carbon, of course. And then doing that, what happens is you form a core shell catalyst. So the shell of platinum and core of platinum alloy. So when that happens, I'm just going to, before I show the equation, you see in this one, chemical potential of platinum in the alloy is low because it's alloy. The chemical potential on the surface is high because it's pure platinum. So eventually a situation can come where there's kind of a quasi-equilibrium and further growth stops. But this keeps on dissolving anyway. Okay. Again, many equations, but I'll just kind of just. If I were to take a particle of radius r0, then its chemical potential is given by this. And I'm just showing you here the A platinum is the thermodynamic activity of platinum in the alloy, whatever that alloy is. When this core shell catalyst forms in situ, then what winds up happening is that in the surface, however, you have a situation where it's pure platinum. And as a result, the chemical potential for platinum of this particle with core shell has this one and no alloying terminate. This is the surface. So eventually time comes when they're about equal, and I don't know if I put this equation or not, but I put it in and just we won't worry too much about it. Okay. If you do that, eventually time comes, this chemical potential become almost near equal, and that happens. Then the radius of these particles become given by this. In this one, this activity of platinum requires two things: concentration of platinum and activity coefficient. I use theta for activity coefficient because I'm using gamma for surface energy. As we know, we typically use gamma for activity coefficient. Here I'm using theta. And this theta depends upon partial molar enthalpy of platinum in the alloy. Here, partial molar enthalpy is of dissolving. We can do the thermodynamics. So you need to measure activity of platinum in PT alloys, and let's say PT3CO. This is most commonly used. It turns out that PT3CO is not very good thermodynamically material for catalyst. Okay, let me mention. Platinum cobalt is not an ideal system. That's because platinum cobalt wants solid solution over wide range. It is much of the range in solid solution. So the activity doesn't change a whole lot until you go to this. And then in addition to that, you have this like a regular solution miscibility gap. So based on if you calculate the thermodynamic regular solution interaction parameter is about minus 2000 joules per mole. So from that, if you have to calculate, it turns out that this value is only 0.75 kilojoules per mole, which means you're not being able to lower activity as much as you would have liked to be. But still, if you put some numbers in, it goes to about minus 119 instead of minus 1 something number that I show you. In the end, I'll show you again those numbers. Okay. So I'm going to show you platinum aluminum system. I mean, you think aluminum is so easily oxidizable, why would anybody think about aluminum? There are reasons for it. So I'm going to say, firstly, there are many platinum aluminum intermetallic compounds, which basically means in this region, which I'm showing the blue arrows, platinum concentration is pretty high, but activity of platinum within the alloy is pretty low. Can do thermodynamic and can. So this should increase stability. Okay? So the different currents are expected to be low. This should increase stability. But we need to determine a core shell catalyst can be formed. The aluminum is easily oxidized. That's the problem. Okay. So the idea is to make a core shell catalyst because of the expense of platinum. So what do we need? We need epitaxially matched platinum shell over the core. So that is epitaxially matched. You want interface that's completely contiguous lattice lines that are contiguous between the core and the shell. Otherwise, you don't want dislocations all as best as possible. One of the most important things that is not understood well is that the tensile stress decreases chemical potential. And one of the best papers I have read, and that's the hardest paper to read, is by called E.A. Flood in Canadian Journal of Chemical Journal of Chemistry. And here I didn't put the slide in. If I were to ask you the following question, supposing this is a saturated solution of sodium chloride. Okay? I'll just give you a simple example. And I put a rod of sodium chloride. It is attached to the beaker, and I put a weight on it so that it is put in tension. And keep it for a while. What do you think will happen? Over a period of time. Intuitively think nothing will happen. But what happens is because the chemical potential of sodium chloride, both sodium and chlorine ions, is lower because you're putting in tension. Sodium chloride from the solution deposits on it. So you pull it, it becomes fatter. It becomes thinner. It becomes fatter. So actually, one of my students did work to do this for platinum, but the complicated geometry. And she was able to show, Priti Parthasari, okay? She was able to show that if you put a platinum of 127 microns to diameter and put away, there's some complicated geometry, but I won't go into that. But put it under tension, over a period of 1 week, it goes to 150 microns. Platinum is being pulled, but it became fatter, not become smaller. And much of the time, many people tend to use strain energy as a part of the chemical potential. And this paper is the most important one, says that strain energy has negligible contribution to chemical potential. And physical review journal is full of all these papers that sticks on talking about strain energy as chemical potential. Unfortunately, this paper has been missed. Okay. Preferred cores are those with larger lattice parameter than platinum, gold, possibly alloy silver, possibly aluminum, but of course aluminum easily oxidizes. So I'm going to just tell you about core shell catalysts for silver and platinum. Okay? What I'm showing you is a schematic. Core is silver, shell is platinum. And because they have the same structure, you can form contiguous lattice lines, coherent interface, I mean, basically. I'm forgetting the terms. So the platinum shell in tension reduces chemical potential, so it increases stability. And so without doing anything, this thing, if I had to use some numbers value, the chemical potential now has gone to about minus 144, 67. So decreased chemical potential, increased stability. So stress has a profound effect on stabilizing Okay. So here are some things that I want to show you. Is that we calculated stability of core-shell catalyst, and the way we define stability is using Nernst potential. So we describe stability in terms of millivoltage. So positive number means better stability, negative number means not. So what I'm showing you here that, okay, if core is platinum and shell is platinum, of course is 0, 0. Sorry, let me just go to 0. If core is silver, the stability increased by 190 millivolts because of the lattice. Now, if you take nickel, nickel has a smaller lattice parameter. As a consequence, actually, it is not that stable. The stability goes down substantially if I use nickel as a catalyst. Now, what I'm saying you is these are the stability we are calculating using thermodynamics and mechanics. Okay? Very, very well-known person in Texas A&M called Parla Balbuena. She's in chemistry department there, and she does DFT calculations, right? And so she had also done DFT calculations. But remember, DFT calculations really don't tell you what's happening. It's difficult to know. Yeah, exact sources. So it turns out, though, however, her numbers are 0, of course. Here, ours are 190, his are 200, 180. 160, minus 400, hers are minus 84, minus 520, minus 600. So one thing is thermodynamics is profoundly important even in a nanoscale. So I'm just showing.
Millivolt values.
Huh?
They're red.
Sorry?
The numbers,
Huh.
millivolts.
Yeah.
100, 160 and something. That is relative to the
Pure platinum. Exactly. So
shift in the Nernst potential.
yeah, in terms of non-potential. So that means if I use nickel as a core and with platinum on it, it will be much less stable than pure platinum. But if I use silver as the core, then platinum is much more stable. The catalyst platinum is much more stable. That's what these numbers prove. So we decided to do this silver platinum core shell catalyst. So this is again on carbon support. I'm not showing it this thing. What I'm showing you here is a schematic of a platinum nanoparticle. And then all we've done is just put it in a platinum chloride solution, okay? And with carbon. Then eventually what happens is some of the silver dissolves. 2 silver reacts with platinum 2 plus to have platinum 2 silver. So some silver is dissolved. And I'm showing you this smaller than these are the platinum ones. I'm showing you this smaller than this simply because the reaction is this. So you have to take away 2 silver atoms to form 1 platinum atom. So it becomes smaller, like slightly more. So I'm just showing some TEM images from chemical analysis. This is kind of crude. It needs to be done. I mean, today with better facilities and maybe even better experimenters who are TEM people, perhaps we could do better. What I'm showing you is the core shell catalyst in mind. This is the core, silver. And if you can see, this thin layer of platinum on it. I'm just showing you. So there's a thin layer of platinum, and this is what I'm showing you. This is silver, and this is platinum. But because of the fact it's a spherical particle, even in the center, there is the cross platinum. So you have to go through platinum shell, through that. So what I'm showing here, chemical analysis is done, and a core shell catalyst. This is the central region. This is the core area. Yes, this is the core area. And this is the platinum, because the platinum is there everywhere. You can avoid that. And this is the peak for silver. And this is our attempt to do the shell. And what we see, the platinum is about the same. The silver seems to be a little bit less. But that's what I'm saying. This needs to be done much more carefully than we did. But I think if we can do with better TM, we might be able to isolate, and so that we can go to really what half a nanometer, 2.2 nanometer scale, and actually do the chemical analysis. We do that. Okay. Now I'm going to talk about particle size distribution. It's difficult to make, when you make these nanoparticles, they're not all the same size. This is average particle size, we know, but they are different size. So I'm going to talk about average catalyst size is 8 to 10 nanometer. Most catalysts are polydisperse. Polydisperse means different sizes. Smaller particles shrink and larger particles grow. Driving force between the two particles again proportional to the difference in the chemical potential, the inverse function of radii. Stability of monodisperse particles, if they are all identical particles, they will be infinitely stable, if you can make them. Okay. First, I'm not going to the details of it, but I'm just want to show you that here what they've done is that supposing it's we decide to take, suppose there are particles, and we're going to say fixed number of atoms. The number of atoms we chose here, I think 642. I can look at it. Am I saying it here? 642. Total number of particles 642. Okay? So when we are here, it means when we go to smaller size here, total number is fixed. At this end, maybe one particle is 640 atom and one has 2. This is an example. So it's easy to degrade. Okay? Now, if I go on this end, we're talking about particles that are very close in number. Both are about identical size. So what that does is I'm putting a logarithm of chemical potential difference. As you go to particles are almost identical size, the chemical potential difference is very, very small. If that's chemical potential difference is very small, they don't want to go because there's no way to transfer. And so I will go in detail, but I think this is a similar plot for different number of atoms. And this is what we call mean field model. I think we use mean field model in everything else, in diffusion much of the time. Again, I want to go to the equations. Forget about these equations. In this equation, total number is fixed, and we will choose a total of 641. Okay. Okay. Again, I'm showing here chemical potential difference against a difference in number of particles, atoms in one particle versus the other particle. So if I'm here, it means there is very little difference between the number. They are almost identical size. If I'm here, it means one particle is very large, one particle is very small. The one particle is small will quickly dissolve and go to this thing. Okay. So anyway, if similar problem here, this is what I want to do stability-wise. That here what I'm showing you here is log of chemical potential difference, and we're taking total of 10 atoms. So this particular particle, chemical, one has 9 atoms, one has 1. This has one has 8, other has 2. This has 7, other has 3. This has 6 versus 4. The difference in chemical potential is very small. If they're all 5 and 5, then it's undefined. Chemical potential is completely undefined. Okay, say this is an example I'm going to show you. It's what was done years ago by this is some work done on platinum clusters on carbon support. And what they observed, if each particle had 68 atoms, chemists have found a way to make almost, they know how many atoms are there in a given particle. To the number one atom, to one atom. So these particular monodisperse atoms, they all have 68. And over a period of time, there's hardly any degradation because they're all 68. This one is polydisperse, which has 52 and 68. That degrades rapidly. And this one has more than 53, and those degrade rapidly. So what this shows is monodisperse don't degrade. The remaining time, I'm going to talk about the role of support and the stability of degradation of platinum nanoparticles. As I said, you have to have platinum particles sit on electrically conducting support like carbon. Interaction between catalyst support, what's called the functionalization, that is wetting, is important. The other is support surface geometry, which I'm going to talk about. Support surface geometry, what profound influence it has. Okay. What I'm showing you here is that if I take a particle of radius r0, and if I calculate its chemical potential 1 nanometer, its chemical potential is minus 120 kilojoules per mole. Okay. Now, if I were to take this same amount of platinum, putting on a support, so that it forms a lenticular shape, where this angle theta is theta, and I chose theta is equal to 30 degrees. So the volume of both of them is identical. It's the same amount of platinum. But because it's lenticular, its radius is r1. And if you, if this precipitation and weighting and study in kinetics class or thermodynamics class, you know that you can actually calculate what the chemical potential is. Okay? The surface energy in those relationships. So the chemical, considering that for angle of, the chemical potential, now for this one, for this situation is minus 141 joules per mole. But if you have just a single particle, it was minus 120. And remember, minus 120 is bigger than minus 147. So minus 147 is good. Minus 120 is not so good. Now talking about again further functionalized support. As I say, I'm comparing this with this situation. Now, as I said, the chemical potential difference radius comes out to be this, relatively, because of the contact angle. But because of the fact that you have surface area of the same particle, the surface area is bigger than surface area here. So technically what winds up happening is that you have an opportunity to increase stability and increase catalytic activity both at the same time. So you can technically assume increase stability, increase in catalytic activity. Once again, I just said, anybody is interested in more, this will be available for a while, right? Okay. So now I'm talking about the catalyst. Talking about here. Sorry. Yeah, I'm talking about changing as a function of theta. It turns out that I'm showing you increased activity when it's really close to very, very low contact angle. Actually, there's a little dip here, and then activity, activity slightly increases again to the. And this I'm showing you here is the durability of it. If it is very, very thinly spread, the chemical potential is so low that it doesn't want to degrade. There's not further way to go to lower state. Yeah, okay. This is some work by Professor Zhang, who he was at Louisiana, now he's at Connecticut. What they did is they studied what's called electrochemical active area, and they conducted this studies on PEMFC cells using platinum on carbon and platinum on titanium disulfide. Now they found and platinum on titanium disulfide has a greater stability. Now let's look at platinum is more stable on TiA to the SC. Expected stronger interaction between platinum silicon than platinum carbon, because there are many platinum silicides that form. So when you large compounds can form, then you have stronger interaction. Many intermetallics in platinum-titanium system. This means a good bonding is expected between platinum and titanium. So it's a win-win situation. And so here, sorry. Okay. This is what I'm trying to show you. This platinum and titanium disulfide before test, platinum titanium after test. This is platinum and carbon before, and platinum carbon on this thing. This TM is not that clear, but they had done some more measurements to find out that there's a growth in platinum particle and much less growth in this case, because platinum interacts with titanium disulfide enough so that it doesn't want to move around. Okay. This is the platinum-titanium phase diagram I wanted to show you. If you look at platinum-titanium phase diagram, see, there are so many intermetallic compounds that if you were to choose compounds on this, if you decide to plot platinum activity, actually platinum activity here is unity at this one. But if you come down because of the compound, it drops rapidly in this one. So you can get low platinum activity in this platinum-titanium alloys.
These intermetallic compounds are all electrically conducting.
Which one?
Intermetallic compounds.
Oh yeah, they are intermetallic. Yeah. Huh? Yeah, they are conducting. Yeah, absolutely. Yeah. And here I'm taking platinum, see this silicon diagram, the same thing. There are a lot of intermetallic compounds, so the bonding of platinum to titanium disulfide is much more easier than to platinum to carbon. Okay. Now, my last topic is going to be support geometry. I think I did to finish in a few minutes. That's good. Supposing you take a support geometry that is a crevice. Okay. By the way, this problem was first looked into not for stability, but nucleation growth by David Turnbull. I'm sure we all know David Turnbull's name. He was at Harvard University. David Turnbull did a lot of modeling work at that time. So now if you put the same material platinum in this same one, but it's in a crevice. Okay? So it turns out angle theta is this. So now the platinum is no longer like this. It's like this. If it's like this one, then actually you are under tension. The platinum is under tension. Okay? So one can go and calculate this thing within the chemical potential calculation as well. And we have looked at, if we have, for example, we took two angles, remember. Let me go back to this one second. Alpha is this angle, okay? This crevice, alpha is this angle, and theta is this angle, the contact angle. As you know, if you take tube and put water in it, water curvature looks like this, because of the wetting part. So it's the same concept. So you can calculate what the chemical potential ratios are, you can calculate what the area ratios are. Area ratio is important because it talks about activity. And it turns out that for the angles that I showed, because there are many calculations I won't go into it. Chemical potential, I is the initial radius of the spherical particle, or plane particle. Chemical potential of this particle in the crevice is now minus 157.75 kilojoules or more. That is lower than for bulk because of the curvature effect. So I'll just mention, compare one thing. Bulk platinum at 300 Kelvin has minus 147 kilojoules or more chemical potential. 1 nanometer particle, radius particle is minus 20 because of the surface and small size. 1 nanometer of PT to CO is minus 190, not much advanced really. 1 nanometer, by the way, core shell is written as core first and shell last. So Ag at PT means Ag is the core and PT is the shell. That's the terminology in the nanoparticle thing. 1 nanometer AgPT is about 1 minus 144. 1 lenticular particle at 30 theta angle is minus 147. A particle in a crevice is minus 157. So platinum crevice low with low contact angle negative curvature, even more stable than that. Now, there's a company, I think 3M, has been doing some work. They don't tell you why they're doing it, obviously it's understandable. But they have developed platinum catalyst for PEM on carbon rods, and it's just this thin layer of platinum on it. So at least it is zero. Okay? This is even better if you could go into catalyst. So platinum catalyst in crevices with low contact angles exhibit negative curvature, even more stable than platinum. Okay, I'll summarize. Lower platinum chemical potential, higher stability, alloy catalyst intermetallic, somewhat stable. Core shell, shelling biaxial tension is what you want. So you want the lattice parameter of the core bigger than that of the shell. Catalyst wetting supports strong interaction, increased stability. Thin monolayer in platinum crevices should be very stable. So what we really like is a rough surface and thin platinum layer inside it. Oh, thank you. Get off my talk.
Let's take some questions.
Yeah.
So you discussed in the slides how if you have too much platinum, it doesn't make it any better. There's a certain
Sorry, I missed the question.
You were talking about how if there's too much platinum, it doesn't make it any more efficient, but you also don't want platinum to be too thin.
But you want, if it is thin, but if it is on a, if it is too thin, yes, on a regular catalyst, it will be bad because it will dissolve away. But if it is thin and you take it across the catalyst support, which is strongly bonded, and also the geometry is the same. So that's the reason I'm saying this 3M company is doing, which I think they have only 2 atom layers on that platinum. But that's because it is thin, but it's spread out in such a way it doesn't want to go anywhere.
Do you know how thick that is with the
2 nanometer. And one of my postdocs, he is now a faculty member in China. He did some work on, not the air, but he wanted to make studies on carbon monoxide areas or chemisorption on platinum. So what he was able to do was platinum layer that had 4 atom layers. 4. And so basically what carbon monoxide adheres to it, carbon monoxide bonds some electrons from it, and the conductivity goes down. Because you don't have enough electrons to flow around, they're just bonded. Yeah, okay. Yeah.
So on the trying to understand the thermodynamics, the chemical potential as a function of
Sorry, go ahead.
I'm trying to understand how what is the nature of dependence of chemical potential
On stress, right?
particle radius.
Okay. Because of fact, the chemical potential has a PV term, right? Pressure volume term, right? And if it's a small particle, then the particle is under pressure. So if you look at chemical potential, much of is because of pressure in it. This free energy has what? PV term in it. And that's exactly the reason why the strain energy is not important. It's pressure that makes the difference, not the strain energy.
The pressure is an internal pressure.
It doesn't matter. Anywhere. You can put it externally. I mean, suppose you take gas, right? You can put in gas and put in a cylinder, put load on it, weight on it, put more and more weight, the gas goes down, chemical potential goes up.
So my question is actually slightly different.
But
In the equation you wrote, in the chemical potential of a particle is the bulk plus.
Yeah. So it's on a molar basis.
Right, no, I understand that part. The question is, the second term
Yeah.
has the surface energy term.
Yeah.
And so the total of it says chemical potential should increase should decrease with increase in particle size.
Chemical one, right?
Total chemical potential.
No, I think his chemical potential is defined on a molar basis, on a mole basis. So what I mean is, if I take 1 mole of platinum and disintegrate it into nanoparticles, then if you look at the chemical potential of that on a molar basis, that's what that is. You see what I'm saying? I mean, if I were to just take one chemical, we're talking about chemical potential on a molar basis. We're not talking about chemical potential of one particle.
Even though you're calculating for a particle,
Yeah, but it basically would mean if I were to take this 1 mole of platinum, disintegrate into 1 nanometer particles, and measure its gift energy, and here I just measure from 1 mole of platinum. Then that's the difference we're talking about. Yeah.
Did you see a decrease in the catalyst effectiveness between the crevice platinum and the actual nanoparticle platinum because of the differences of size?
No, sorry. My hearing isn't good, so.
Oh, sorry. Did you,
No, you're not. Yeah.
did you see a decrease in the effectiveness of platinum as a catalyst using it in the crevice from the smaller surface area versus the nanoparticles, which
I shouldn't hear the question. I apologize. What is the comparison you're saying? I didn't get the question, sorry.
Oh, all right. Did you see a decrease in how effective the platinum was as a catalyst
Oh, yeah.
in the crevice versus the
Oh, no, we have not done that. Experimentally not done it. No, we have not done it experimentally. But I think the 3M company is doing it. And they have been doing this for 15 years. So, yeah. The experimental evidence for it.
I think his question is, if you've reduced the surface area, even though you put it in tension, are you really ahead as opposed to keeping these where you have lots of surface area?
But the surface is increased, not decreased.
So the thickness is very thin.
Yeah, very thin. Yeah, sir.
For the core shell particle, was the purpose of the cores just to put the surface of tension, or was there
Core shell particle, original purpose is to reduce the cost. But if as to what choice of core you have will determine what the chemical potential of platinum is in the shell. And so our study shows that if you were to put this in silver and put it, because silver has a larger lattice parameter, is thinly spread over it and is in tension.
Does room temperature creep occur?
Huh?
Does room temperature creep occur? Do those stresses relax?
No. I think the creep is almost impossible to occur because all epitaxially matched. So to creep to occur a dislocation movement and those kind of things. No. Of course, I had to study that stability is not been studied for long enough time. But at least one thing, the Toyota Mirai car PM fuel cells have been shown to cell stack to last at least 7-8 years. Yeah. Of course, like everything is, performance goes down, but there are electronic balancing circuits that allow you to still use it. Yeah.
So for that crevice, what was the substrate?
In this case, it is arbitrary substrate. So what I'm saying is that some substrate support that has certain weighting characteristic that it will be in.
The PEM companies, anyone using these concepts in?
They're using it, not going to tell us. That's the reason when during Obama's term, DOE put out this, Stephen Chu was the energy secretary, they put out these big contracts for lithium-ion battery, when Sony has been making it for years. There was no need for much of the research, and after 10 years they cancelled it.
So can you talk a little bit about your entrepreneurship and what was rewarding to you and where VersaPower is today?
I think, I think starting ceramic with Professor Gordon was, of course, very, very useful, basically. And there I don't want to take that, I don't say that I took the lead or anything, but I was one of them. And that was really rewarding, to be honest. Later, Dinesh and myself, when ceramic no longer qualified for SBIR, when I was brought over by, what's the company? Norwegian. LCAP. When they were, so Dinesh and myself started MSRI, and much of it was, there's some other contrast, but quite a bit of SBIR's contrast. And I think survived 28 years, right? I mean, just not bad. I mean, Enron did not survive that much. So it survived longer than Enron. And then we started nano oxides, but what happened was, and we were getting a lot of orders from nano oxides to get powders. We had a molecular decomposition process for making oxide. We were getting a lot of orders from Europe. But then the 2009, 2008, that downturn in economics, suddenly orders stopped.
For those graduate students who are thinking about doing a professorship, can you talk about a little bit about the requirements of being a professor?
Of course, I think one thing I would certainly say is that focusing on what you want to do and enjoying what you want to do is probably the most important. Now I don't work as hard, but I remember for years, on Sundays I used to look forward to Monday. I had something in mind that I wanted to do that. And I had to really say that I'd learned from modifying over the years. And when I did my PhD was with Lee Johnson, but the funding was all modifying. And because Lynn was a young faculty member at the time, so funding was from modifying.
So again, along the same lines, like another aspect of academic career, as a scientist, as a professor, is learning.
Okay. I'll tell you one thing as I forgot. One of my great mentors, and I forgot, this is what happened with old age, is Richard Boyd, Dick Boyd, okay? The reason was, when I first came here, I did my PhD in fractional mechanics of ceramics. And if there is some course that needed to be taught, Dick would ask me, Anil, will you teach it? So he kept on giving me all different courses. And one day, in the late 80s, one day Dick walks in my office and says, one of the faculty members was leaving, and then I want you to start teaching statistical thermodynamics. So I started preparing notes for that. And to me, my teaching drove my research. My research didn't drive my teaching. So it allowed me to do different things at different times. So if I did in advice, I would give teach as many different courses as you can. You learn through teaching, and you learn to do research because you're taught that. Oh yeah, right.
These days of computational,
I think
a lot of computational, there's a beauty of working out by hand. It increases your thinking about the problem.
Oh yes. Actually, okay. Yeah, I'll tell you a recent example. But in 2014 or so, I had calculated, supposing if you to put a pore in UTS stabilized zirconia, and I found electrochrometry to pressurize it, and to calculate pressure distribution on those kind of things. And but then I also was doing a calculation that if I can do it electrochemically, technically I can do is take a pore, put a thin cylinder on top, which is pore, and pressurize it like this. And those answers were not coming together. And I was at one of these conference called Telluride, Telluride conference. At 2019, I was in that conference. And suddenly, while sitting, it dawned on me what mistake I was making. Okay? As soon as I came back, within half an hour, I solved the problem. And then myself and Ken reached my, because of the fact that I didn't know where to publish it, because if I sent to Electrochemical Society, not many people understand mechanics. If I sent to mechanics, not people understand electrochemistry. So myself and Ken reached Schneider, Ken reached Schneider? UT Arlington. So we wrote a chapter in a book of that. But it took me, I think I was just going through my head for 5 years, and suddenly. Okay, thank you. Thank you.
Thank you. That was great. Wow. That's so fun to see all the different aspects of involved in that. Yeah.